So let me check who else is joined. If anyone else has joined, no. Let's wait for 30 seconds and then we are going to start. Chalo, it's 5:54. I think we should start now. Okay. So today is about convection. Okay. Today class, I think it will be slightly long. We will try to cover everything in time. So my speed will be little faster, but I'll mark the important points, whatever the important, formulas or, results that are there. I'll start marking them. So you have to focus more on that because there will be so many things that of course are important but not important from exam point of view. Okay, chalo. So what is the objective of our analysis when we study convection heat transfer? What is the objective? So I have told you that H basically is a function of so many parameters: velocity, characteristic dimension, density, mu, Cp, okay, thermal conductivity, and these values are defined experimentally. It is not a property of either the fluid or the solid. It is basically a function of fluid properties as well as the flow conditions. Okay, now, so it is where the whole analysis of convection analysis is done to determine H. This is the main objective. Whole analysis is done to determine H, heat transfer coefficient, convection heat transfer coefficient. Okay. Usually in question, they directly give you H. But when you go for research, when you go for other higher studies, then the focus is how to determine H. So in this short study of convection, in these 5, 6 hours, 7 hours, we are trying to understand what is the basis of this analysis. There, of course, we will not go much in deep, but at least we will get an overview of the things. Okay. Now, once you have determined this H, then you will need to determine convection heat transfer rate by using Newton's law of cooling. Okay. So, what actually happens? Let's say this is your solid body, and fluid is flowing here at u infinity, which is free stream velocity, and temperature is T infinity. Okay. Now, when this fluid is flowing, this fluid will take heat by convection or give heat. If this T surface is greater than T infinity, then heat will be taken away by the fluid because plate is hot. Now, how do you determine convection? Q dot HA T surface minus T infinity. Now the whole thing is to determine this H. Once you have determined this H, then you can calculate Q because all other parameters are fairly simple. Okay, so most of the analysis is based on this. Now what is free convection? We all know free and forced convection. Free convection is that basically happens because of density difference, which happens due to density difference or the buoyancy forces. So buoyancy forces are coming because of the density differences. Okay. So for example, let's say you have this plate. Now if fluid is flowing in any direction, whenever it is going to take some heat, it will move in upward direction. If the heating is taking place, the fluid will move in upward direction, If this is a hot plate, that means heating of fluid is taking place. Hot plate is there, that means fluid is getting hot. Fluid is getting hot. Okay. And we all know the fluid, for example, air is the fluid. Then we can apply PV is equals to mRT. P is equals to M upon volume RT. P upon density RT. So whenever temperature is going to increase of the fluid, yes, what happened, Shruti? Okay. Do you have any question? Okay. Chalo. So whenever temperature is going to increase, the density is going to decrease. If density is going to decrease, then fluid will move upward. The fluid will move upward. So usually velocity is not a very significant factor. Heat transfer is not happening because of velocity, is happening because of movement, and movement due to density change. Density is decreased, that's why fluid is moving upward. If the fluid is getting cold, for example, hot fluid is there, it is flowing over a cold plate. So that means temperature of the fluid will decrease and it will flow downward. So anyway, the movement of fluid is happening, but velocity is not very significant. Velocity is not very significant. Okay, these type of heat transfer are called as free convection. Forced convection, we all know, here we have a significant velocity and we try to increase the velocity by using some external force, pump, fan, blower, etc. Okay, now when we talk about forced convection, we talk about two things. What? First is external flow. External flows, which is basically a flow over flat plate. Outside it is happening, flow over flat plate. Okay, then the other is internal flows. Now internal flows is flow through pipes or ducts. Flow through pipes or ducts, rectangular ducts. Okay, here also we have open channel as well. What do you mean by open channel? By, if for example whatever dia is there, it is not completely filled. Okay, if this is a dia of the tube or pipe, it is partially filled. Yes, there will be free surface. Very nice. So it is partially filled and this is your free surface. Okay, so our focus will be on two things: external flow A and internal flow B. Today we will only be able to cover external flows, but so many things we need to do before we go to external flows. The same thing we are going to utilize the internal flows. So internal flows will not be that bigger thing. Okay, we will directly apply what we will learn today, but today we will only be able to cover external flows. External flows. Okay, chalo. Now, the problem with whole analysis of convection is this: heat. How to determine heat transfer coefficient? This is the major issue. How to determine heat transfer coefficient? Okay, the whole analysis is based on this. Now, so as I have told you many times, h is a function of velocity, characteristic dimension or characteristic length, density, mu, cpk. Now these are thermophysical properties of fluid. Thermophysical properties of fluid. These are flow parameters. Flow parameters. Okay, and we know what all of them. V is velocity of the fluid, meter per second. D is characteristic dimension. Okay, how do we determine this? DH is equals to 4 area by wetted parameter, perimeter. D is density kg per meter cube, mu is dynamic viscosity of fluid, Cp is coefficient of specific heat or specific heat coefficient, and K is thermal conductivity of material. Here, let me define nu as well. Nu is kinematic viscosity. Kinematic viscosity, which is equals to mu upon rho. Mu upon rho. Okay. Now, the problem with this is that H is a function of many dimensional parameter. And now when you do experiment, many dimensional parameters, variables or parameters. Now when we start experimenting, so it's very difficult to determine precise value of each parameter. And then whenever one parameter changes, it is going to affect other parameters as well. So what to do? So what we do, we do a dimensional analysis, dimensionless analysis, and we determine H as a function of very few dimensionless variables. So it's not easy, but still it reduces some of our work. Okay. So first of all, we are going to start dimensionless analysis. But before that, I need to understand how to determine characteristic dimension of a body. Because sometimes you will get issues in how to determine this. Okay. So we usually say DH or sometimes D or whatever. Sometimes in some books it will say LH or simple L. Okay, chal. Now first, if you have a flat plate, and for example something like this, and fluid is flowing like this at V infinity, then can you tell me what will be the DH? Yeah, it is length of the plate. Parallel to the flow. Very nice. Okay. Then second, I'll try to go a little fast. Okay. So circular, if we have circular duct, otherwise we will not be able to finish even in 3 hours. Circular duct. So tell me, circular duct. If this is my circular duct, this is diameter, and flow is happening like this, V infinity. Then dH will be equal to diameter. You can also calculate this for area by, and this is cross sectional area. Okay, weighted parameter. Okay, so it is 4 into pi by 4 d square upon pi d. So if you do that, you will get 4 pi dd. It is d. Yes. Third is, if you have a annular flow. Annular. Do you know annular? What do you mean by annular? Yes. So if it is hollow, but annular space is the space between these two pipes. Okay, so this one, blue one is a solid pipe. And flow is happening here in the annular space. Here it is happening. Yeah, gap between two pipes. Yes. So here DH will be equal to For area is what? By pi by 4 d out square minus d in square. And this is pi d out minus d in. So what do you left with? D out, yes, minus D in. Very nice. Very nice, Sean. Chalo. Then let's say we have a rectangular duct. We have a rectangular duct. It is DH. DH is 4 cross-sectional area by parameter. Yes, that is right, Shruti. DH is equals to 4 cross-sectional area by weighted parameter. Okay. So rectangular duct. What is rectangular duct? For example, it is like this. Okay, and flow is happening in this direction. So let's say this is your A and this is your B.
Hello, sir.
What is this? You are asking something? This one?
Hello, sir. Yes. Like here, is the perimeter D out minus
Just
D
one
in or
second.
D?
Yeah.
Hello, am I audible?
Hello.
Sir? Sir, here the perimeter is it D out plus D in, like or D out minus D in.
I am sorry. I am not able to understand. Could you please? It's not clear what you are saying. D out minus D in, no? Why plus? What you are saying? This is whole area. This is your whole diameter. Now you have subtract the inner diameter out of that. So that then only you will get this area, right? You are trying to find out this area.
Sir, it was
This
D naught plus DI, sir. Means final result you write the minus, sir. Actually, it was plus only.
Okay.
Final,
Sorry.
D,
Yeah, that is
D
yes. Okay. That is right. I'm sorry. That is right. Yes. Thank you. Chalo. That is right. D naught plus Di. Yes. D out minus D in get cancelled and only D out plus Di will be left. Okay. Chalo. If this is your duct and this is what it is happening. Okay. A and B we have defined. So again now DH will be equal to DH 4AB upon 2A plus B. So it will be 2AB upon A plus B. Okay. If it is a square duct, that means square duct means A will be equal to B. A will be equal to B. So you can modify this. It will be how much? By 4A square upon 4A upon 4A. 4A, it will be equal to A. It will be equal to A. Last is if it is happening over a sphere, for example. This is a solid sphere and this is how the flow is happening. So can you tell me what is DH? Can you tell me what is DH? Yes, it is D. Very nice. It is D. Okay. So you will use this DH in Reynolds number very frequently. So it is a good idea that you know how to calculate for at least these bodies. Okay, because very frequently in Reynolds number you will use that. Okay, chalo. Now, as I told you, we need to do dimensional analysis in order to define H into few dimension-less parameters. Okay. So how do you do dimensional analysis? Of course, we are not going to do dimensional analysis. It is not at all required. I will directly give you. Okay. So dimensionless analysis is a mathematical technique which convert dimension parameter or dimensional parameter into dimensionless parameters. Sean is typing something. Let me see what he is saying. Okay. Now, what is the objective? So, objective is to combine variables or dimensional variables into dimensionless group, Reynolds, Prandtl, Nusselt number, and then to determine convective heat transfer coefficient. As I told you, by convective heat transfer coefficient is a function of so many dimensional parameters, which is very, very complicated to design. So by using dimensional analysis, we are going to convert those dimensional numbers, in fact, many dimensionless numbers, into very few dimensionless numbers. Okay. How do we do that? By using Buckingham Pi theorem. Okay. So it says if there are n total number of variables, both dependent and independent. So how many variables are there? 1, 2, 3, 4, 5, 6, and 7. We have total 7 variables. Both combined, both dependent and independent. And M is the number of fundamental dimensions. So how many M? M is M, L, T, theta. Okay, this is mass, length, time, and angular, if there is any angular variation. Okay, but we do not have angular, I think. Then the functional relationship among the variables can be expressed in terms of n minus m number of dimensionless pi terms. Theta is, yes, I think it is temperature only, which we have defined earlier, T minus T naught, something like this. Or I think it is angular. I'm not very sure actually. I would have to check this. But anyway, I don't think we are going to use theta for our analysis. Okay, chalo. Or if we do in internal flows, that I'll take a look. Okay, chalo. Kya was Shruti? What happened? Okay, right. You will get this. Why? What are you writing? You will get the PPT anyway, no? I am not writing anything. What are you writing? Chalo. Now, the total number of pi terms will be n minus m. So, 7 minus 4 is equals to 3. So, we will define our analysis into three-dimensionless variables. 3 for forced convection, 3 for forced convection, and 3 for free convection. Shruti, can we move? Okay, ठीक है, चलो. Now, of course, we are not going to do dimensional analysis. There is no point in doing that. At least for GATE, there is no point. ESC, yes. Sometimes in conventional exam, they ask you. But for GATE, there is really no point. Okay. By doing that, we have defined Reynolds number, Prandtl number, and Nusselt number. And these are dimensionless numbers in forced convection. Very important that we are talking about forced convection. We are only talking about forced convection. Okay, Reynolds, Prandtl, and Nusselt number. Okay, so let us see them one by one. First is Reynolds number. Reynolds number is defined as the ratio between inertia forces and viscous forces. So you all know what is inertia forces. What is the inertia forces? In general, what is inertia? Can you tell me what is inertia? Yes, force due to acceleration. It basically forces you to remain in the state of motion. Okay, or whatever state you are in, yes, mass into acceleration. Okay, chalo. So it is kind of a driver, and viscous force is basically resisting the motion. It is resisting the motion. It is trying to drag you because of the viscosity. So it is kind of a resistance to motion. Resistance to motion. Okay. So I can write inertia forces as d by dt mass into velocity. And this I can write shear stress. Viscous force is what? Shear stress into area. Shear stress into area. Okay. So I can write this mass flow rate also and velocity. And this is shear stress. Do you know this shear stress you have studied in fluid mechanics? Newton's law of viscosity. So what is that? What is shear stress? Mu du by dy. Yes, mu du by dy. Okay, into area. Chalo. So this is mass flow rate, or let me convert this into by density area into velocity, and we have one more velocity, so it is square. This is mu du is basically final velocity and initial velocity is 0 by y in the y direction. So we are going to say dimensionless L or D into area. Now we can cancel velocity. Okay. So rho a v square upon mu v area by d. Okay, velocity and velocity get cancelled, and finally you will get Reynolds number is equals to rho v d h. This is your characteristic dimension upon mu. You can also determine this. In terms of kinematic viscosity. Okay, because we know kinematic viscosity is equals to mu upon rho. So it is vdh by rho. vdh by mu. Okay, so d rho is density kg per meter cube. V is mean velocity. dh is characteristic dimension or characteristic length. Characteristic dimension. And mu is viscosity. Dynamic viscosity. Okay, and mu is kinematic viscosity. Okay. Now it is very important to understand that. Let's take this formula. Okay, now rho and mu, they are fluid properties. So once the fluid is fixed, fluid properties, once the fluid is fixed, they are fixed. And dh is the characteristic dimension or diameter. Let's say if it is a tube, then it is a diameter, or whatever it is characteristic dimension. So these parameters are fixed. You cannot do anything about it. The only variable that we have is velocity. So velocity is going to impact the inertia and viscous forces. For high velocities, that means inertia forces will be greater than viscous forces. Yes, chalo. Now, based on velocity, high velocities and low velocities, Reynolds number will determine if the flow is laminar or turbulent in forced convection. Okay, very important. Determine if the flow is laminar or turbulent in forced convection. Very important that it is Reynolds number is a dominant number that tells you if the flow is laminar or turbulent in forced convection. In free convection, Reynolds number does not tell you this. There is another number that tells you this. We will talk about that. ठीक है, चलो. So what about critical Reynolds number? Laminar. So let's talk about pipe. If we are talking about duct or pipe, then Reynolds number should be less than 2000. Sometimes this number is 2300. Okay. For flat plate, it should be less than 5 into 10 to the power 5. And agar sphere is there, which is, it is not very important, it is not asked, then it is in the range of 1 to 10. Sphere is not very commonly asked, but anyway, chalo. What about turbulent? Reynolds number should be greater than 4000. Here it should be greater than 6 to 6.5 to 7 into 10 to the power 5. Okay. And इनके बीच में there is a transitional flow. From 2000 to 4000, there is a transition flow. Laminar to turbulent transition is happening. Okay. Because flow is not, instantly converted from laminar to turbulent. Laminar is what? The flow, I think I am not going to cover this because you have all studied this in depth in fluid mechanics. Laminar is when viscosity is very dominant, fluid flow as a layer, one layer, then another layer, then different layer, then different layer. Turbulent is intermixing, random, rapid intermixing is taking place between layers. Okay? Okay? Is it clear? This much is clear or not? Chalo, let's move on to the next number, which is Prandtl number. So it is the only dimensionless number, which is the property of fluid defined as the ratio between kinematic viscosity of the fluid and its thermal diffusivity. So kinematic viscosity is nu, thermal diffusivity is alpha. Now we all know how can I determine nu? What is nu in terms of dynamic viscosity? Tell me. Today I am not asking much feedback from you because I need to cover a lot. Yes. Alpha is what? Thermal diffusivity. Do you remember what was it? What was it? Okay, I'll write it down. K upon rho Cp. Rho and rho will get cancelled and it is mu Cp by K. Mu Cp by K. Yes, Shruti, that is correct. K upon rho into Cp. Yes, that is correct. Okay. Now, what is this upper thing? Upper numerator is basically momentum diffusion. Momentum diffusion. How the momentum is diffused during convection. And this is thermal diffusion. Thermal diffusion. If conductivity is high, that means of course the heat will flow to a larger depth. If velocity is high, then if velocity is high, then momentum diffusion will be high. Okay, chalo. Now, if Prandtl number is greater than 1, if it is greater than 1, that simply means what? That thermal boundary layer, we will talk about this thermal boundary layer and hydrodynamic boundary layer. Thermal boundary layer is thinner than hydrodynamic boundary layer. Okay, I'll tell you what. I'll draw a diagram here. Look, this is your flat plate, and if fluid is coming with a velocity u infinity, then a thermal boundary layer will be formed. We'll talk about this, do not worry. Like this. This is your thermal boundary layer, and this is the thickness. At every point, this is the thickness of, I'm sorry, this is hydrodynamic, not thermal. I'm sorry. Hydrodynamic boundary layer or velocity boundary layer. Okay, hydrodynamic boundary layer. Now, due to temperature differences, for example, this fluid is coming, it is at T infinity, and this is at T surface or T wall. Okay, Now, because of this, there is also a thermal boundary layer that will form. Again, we will talk about this, do not worry. And this is the thickness of thermal boundary layer. So it is saying thermal boundary layer is thinner. Like if you want me to draw this on the same diagram, then that means it will be your hydrodynamic boundary layer. For case 1, if Prandtl number is greater than 1. Okay. Now, if Prandtl number is less than 1, then thermal boundary layer is thicker than hydrodynamic boundary layer. Okay. So this is this case. And then I am saying it is thicker. That means this will be your thermal boundary layer. So this one is this case. This one is this case. So it basically tells you that which phenomena is dominating. If velocity is diffused to a larger length or larger thickness, or heat is diffused to a larger thickness, larger length. Okay. So it signifies the relative magnitude of momentum diffusion, or I can say velocity diffusion and heat energy diffusion rate that are occurring through the fluid layers in the normal direction. Normal means y direction to the plate simultaneously in the respective boundary layers. Okay. So look, Prandtl number for air is in the range of 0.65. So it is less than 1. It is less than 1. So what does that mean? Can you tell me? If it is less than 1, what does it mean? Yes. dH is greater than dt. That is right. Thermal boundary layer is, no, it is less than 1. No, it is thinner than hydrogen boundary layer. First one. Yes, yes, that is right. That is right. You are right, actually. It is less than 1 means it is thicker. That is right. I'm sorry. Okay. And third one is Prandtl number of Hg. Liquid metal also, we call it liquid metal. It is very low because it is very, very low, actually. Because conductivity is very high for Hg compared to liquids. Okay, chalo. Next is Nusselt number. Nusselt number. Now, what does Nusselt number tell you? It tells you which of the phenomena, conduction or convection, is dominating in the fluid. In the fluid, which one phenomena is dominating? Okay, so it is defined as the ratio between conductive thermal resistance offered by the fluid and station, if it is stationary, and surface convective resistance. You can also write it in the form of convective heat transfer upon conductive heat transfer, because here we are talking about resistances and heat transfer is inversely proportional to resistance. So this is also we can write. Now tell me, what is conductive heat transfer? What is conductive resistance? Conductive resistance. Conductive resistance is yes, 1 upon LKA. L upon KA. L upon KA. And this K is K of fluid. Very important. It is K of fluid. Then convective resistance is 1 upon HA. HA. So area and area will get cancelled. HL by K of fluid. HL is basically, here is characteristic dimension, K of fluid. Now, if you remember, there was one more number that has the same formula, hd by k. What was that? What that? Do you remember what was that? Do you remember what was that? HLC by k. Maybe if you remember, HLC by k. It was Biot number. I see that you do not remember. But the difference between Biot and Nusselt number is it was for solid. And here we are talking about fluid. Here we are talking about fluid. Okay. Now, as we know that K of fluid is always very low. Fluid usually, solids have high thermal conductivity. Fluid, K of fluid is usually low. And therefore, by this formula, I can say Nusselt number is mostly greater than 1. Mostly greater than 1. Okay. So Nusselt number is equals to 1 for a fluid layer represent heat transfer across the layer by pure conduction. Pure conduction. Okay. And if it is very large, that means convective will be more efficient. So larger value of Nusselt number will tell you by default. Look at this formula. If larger values of Nusselt number is there, means Nusselt number is very high. That means convection heat transfer is dominating. If very small values are there, that means conduction heat transfer is dominating. Okay. And if it is equals to 1, that simply means that Q dot convection is what? Q dot conduction plus Q dot advection upon, I hope you remember this, I have told you this. So this is basically 0 and conduction will get cancelled. Nusselt number will be equal to 1. That simply means the heat transfer is happening because of conduction. Do you remember this or not? Convection is equals to conduction plus advection. Shruti, Sai, were you there in the first class? I think first or second class. Okay, chalo, theek hai. So if it is equals to 1, simply means that only conduction is, heat transfer is taking place. So what is the physical significance of Nusselt number? It is going to tell you that which of the phenomena is dominating in the fluid heat transfer, conduction or convection. Conduction or convection. ठीक है, चलो. Now, those three numbers were dimensionless numbers that are used in forced convection. Now, what about free convection? Here also we have three numbers: Grashoff's number, Prandtl number, and Nusselt number. Grashoff's number, Prandtl, and Nusselt number. Okay. Now, this is something that we already know. We are not going to discuss. We will only discuss Grashoff's law. Okay. Chalo. So Grashoff's number approximates the ratio of buoyancy to viscous forces acting on the body. Okay, ठीक है. I'll take 1 second. Don't worry. Which slide? This one or the last one? Okay, ठीक है. Chalo. Now you see something. Look, inertia forces is a function of velocity, and for free convection, as I told you, that velocity is not very evident. Velocity is usually low, and therefore inertia forces are much less than buoyancy forces, because in free convection buoyancy forces dominate. So sometimes, not always, but in fact mostly you will see that Grashoff's number they will give you as buoyancy forces upon viscous forces. So this is most commonly accepted definition, but usually in very standard books you can get, not the standard, actually the standard book this is given, but books that are mostly scientific, research based, in that this is given. Okay. Now Grashoff's law is equals to inertia force upon viscous force into buoyancy force upon viscous force. Now this is what? This is Reynolds number. Okay. And buoyancy forces upon viscous forces. Now what is buoyancy forces? Buoyancy forces is mass into buoyancy acceleration. Buoyancy acceleration. This is mass only, not m dot. And viscous forces, we already know, shear stress into area. Okay, so we can simplify this by Reynolds number is rho VL by mu into, this is mass is equals to density into volume, and buoyancy acceleration is given by isobaric volume expansion coefficient G and delta T, change in temperature, upon mu du by dy into area. Now this is L cube, this is L square, everything else is same. So now we can cancel it. We can cancel things. What we can cancel? By L, I think L we can cancel. So Grashoff's number that you are going to get is, by 1 rho square is there. L square will get cancelled here, but 1 L is here, so L square will be there. L square will be there. And beta G delta T by V upon mu square. This is velocity by L. Yeah, this much is left. So velocity and velocity will also get cancelled. Rho square L cube beta G delta T upon mu square. Okay, I think this is correct. I think this is okay. I think this is how we give Grashoff's number. Okay, so Grashoff's number tells you rho square L cube beta G delta T mu square. Okay. Now you see, in the force convection, we talked about inertia and viscous forces. Now here, what is the driver? Here driver is buoyancy forces. So now this is significant is because Grashoff's number tells you if the flow is laminar or turbulent. In what? Forced or free? In free convection, yes. In free convection. Okay. So it signifies the effect of magnitude of buoyancy forces. Okay, chalo. Now we have come to one of the main topics of external flows. Okay. So I will start saying things. I wanted to draw this diagram. Now I have animated it just for your convenience so that you will understand it properly. Okay. Chalo. So we are talking about external flows, and hydrodynamic boundary layer means boundary layer that is formed because of velocity gradient. Differential equation of beta. You mean that volumetric coefficient? Okay, definition of beta. we will see that tomorrow. We will see that tomorrow, and when we start free convection. Okay. Actually, I have not added it, but I'll try to add that. Okay. Because today we are focusing on forced convection and external flows. Tomorrow we will come on free convection. First of all, we will start with internal flows, then in free convection. Then we will start talking about that also. I will. You want definition of beta, right? That is what you want. I will introduce that. Okay. I did not. I don't think I added that, but I'll do that. Okay. Chalo. Should we move on, Vijaya? Okay, chalo. So, okay, let's see. This is a flat plate. This is a flat plate. Okay. Now this point is called as trailing edge. This point is called as trailing edge. From here, we are going to define our coordinate x and y. Okay. So over this flat plate, I have defined my x and y. So at this point, x is equals to 0, y is equals to 0. If we go in horizontal direction, then we will increase x. If we are going in upward direction, that means we are going in y direction. Y is positive. If we are going in horizontal forward direction, that means x is positive. Okay, chalo. A fluid is flowing. Now this fluid is flowing with u infinity. This is the free stream velocity. What do you mean by free stream velocity? By free stream velocity is the velocity that is undisturbed by viscous effects. Free stream velocity. Free stream velocity is the velocity that is undisturbed by viscous effect. So whenever this velocity, whenever this fluid will come in contact with a solid plate, then it will have some viscous forces that we are going to talk about in some time. Okay, chalo. It is free stream velocity. Free stream velocity. Okay. Now, what we are doing, we are assuming we are going at a certain distance x. We have taken a certain distance x. Now what will happen? Look, when this fluid, of course, it will be flowing at the surface of this flat plate, right? It will be flowing at the surface of the flat plate. Now at the surface of the flat plate, when the whatever layer of this fluid is going to be in contact with this flat plate at this point, it will stuck at this point. Here velocity will be 0 or u will be 0. U is the intermediate u is the instantaneous velocity at any particular location and point. So here u will be equal to 0. Why it is no slip condition. The layer at every point, you not just here, at every point here also u will be equal to 0. The whole layer that is in contact, the whole fluid layer that is in contact of the flat surface, at every point, that means at y is equals to 0, u is equals to 0 because of no slip condition. Because of no slip condition. Okay. And you can also see this example. You see, for example, you have a declined plate. Okay, it is in downward direction. Now if you drop some water on this plate, then on the surface one layer will be attached to the plate. The upper layers will be moving, but the layer that is attached, that is adjacent to the plate, will be fixed. It is not moving. The velocity, the particles that are at this flat plate will have 0 velocity. So one layer will be at 0 velocity because of no slip condition. Is it clear? Chalo. Now as soon as we move upward, like we are moving in this direction, so the upper layer will have some velocity. You move further up, it will have some larger velocity. Then you move ahead, it will have some further larger velocity. So you see each, now this is at u is equals to 0, this point, and then as you are going up, velocity is increasing. But because of the viscosity of the fluid, this lower layer is dragging. One second. Okay. Let me draw some. Now I am just, making it big so that I can explain things. Now you see, here u is equals to 0 at this point, u is equals to 0 at this point. But as you are going up, u is increasing. But because of viscosity in the fluid, this lower layer is dragging the upper layer. This lower layer is dragging the upper layer, lower layer is dragging the upper layer. Okay. So that means it is decreasing it is dragging itself, dragging the upper layer to decrease the velocity. Okay, and as you are going up, this slowly the velocity keep increasing, and at a certain point, for example, it is increasing here, right? It is increasing here, but now it is not increasing. Now it is not, now because the effect of this no slip condition and viscosity are not very significant. Now it started moving at u infinity. Now it has come at u infinity. Look here, u is much less than u infinity. Here u is less than u infinity. Here air is, let's say, this much less. Here it is this much less. But here it is almost equal to u infinity. Let's say 99% of u infinity. And here it is almost equal to u infinity. Now, after that, you see here at this point, the velocity is changing in y direction. It is called as velocity gradient. Velocity is not constant in y direction. We have a velocity gradient in y direction. But here, after this point, after this point, du by dy is equals to 0 because there is no velocity gradient. There is no velocity gradient. All the velocities u2 minus u1 is same. Okay. If you are going, if u2 minus u1 by y2 minus y1. So this is same. This is u2 is equals to u1 after a certain point. So it will be equal to 0. So du by dy is equals to 0 after a certain point. Okay, so do you understand this much? Do you understand this much point? Okay, now if you understood this, so this profile is formed. It is called as velocity distribution, and this is parabolic distribution. Okay, velocity distribution or velocity gradient. Okay, now if you understood this, if you have understood this, then let me rub this. Okay, do you want to, I'm sorry, do you want to write it down? In fact, leave it. I'm going to show you anyway. I just wanted to explain few things. I will explain this again one more time. Okay, chalo. Now, so because of this no slip condition, here u is equals to 0. Because of the no slip condition, at this point, u is equals to 0. Now, as you are going up, your velocity is increasing. Okay, and velocity is increasing, and this will be your velocity distribution. This is your velocity distribution. So here u is changing in y direction. Okay, and this is called as velocity gradient. Velocity gradient. And the viscosity, because of viscosity, there are some shear stresses as well. So these shear stresses are given by tau is equals to mu du by dy. Mu du by dy. Okay. Now at a certain point here, u is equals to 99% of u infinity. Now after that, velocity is not changing in y direction. Here it is u infinity, here it is u infinity, but below that it is less than u infinity. Now if I talk about a lesser x, like for example somewhere here, lesser x. Okay. So what will happen? You see this profile, because the further you go, the in x direction, this, this profile is going to be more and more linear, because here it is u infinity, and very near to x is equals to 0, very near to the leading edge, you have more influence of velocity, and that's why it is more thicker, okay. Now here you will reach this u infinity point somewhere here much earlier, okay, because velocity is high here, so you will reach this point much earlier at this point, okay. And as further you go, this point will be more further, somewhere here, let's say, okay. So these are the points. Now I can do this at every x, I can do this, and then I can join all the points where u is reaching at u infinity, and this will be the profile, okay. This was this point, not that point, and this is this point, not that point, okay. Anyway, it does not, I mean, once you will join all the points, you will get u is equals to all the points where u is equals to u infinity, okay. You see, u is equals to 99% of u infinity. Sometimes I am going to say this as u is equals to u infinity, okay. It does not matter. Is someone saying something? Okay, ठीक है, चलो. So if I join all these points where velocity, so you see in below this, and this is called as hydrodynamic boundary layer. Now in this region, below the hydrodynamic region, okay, all this region, I don't know, I don't want to, make a mess in this diagram, but let me draw it here. So if this is my flat plate, this is my hydrodynamic boundary layer. Now in this region, we are observing a velocity gradient. But outside this region, velocity gradient is equals to 0. Velocity gradient, yes. So because there are velocity gradient, they are because of the viscosity, and it is called as viscous region. That is also right. Okay. Chalo. Is this much is clear or not? Okay. Now the point. So hydrodynamic boundary layer, this is my hydrodynamic boundary layer, where it is showing the velocity gradient near the flat plate, is defined as the thin layer formed over the flat plate inside which velocity gradient are seen in the normal direction. In what direction we are seeing velocity gradient? In y direction to the flat plate, okay. The velocity gradient are formed due to viscosity of the fluid. Now the thickness that is takes, okay, from this point to this point, the thickness that it is taking from u is equals to 0 to u is equals to 99% u infinity is called as boundary layer thickness. Okay, so this is called as boundary layer thickness. Now at y is equals to 0, u is equals to 0, and y is equals to delta H, which is boundary layer thickness, U is equals to 99% of U infinity. Is this clear? It is arbitrarily defined as the distance measured perpendicular to the plate surface at which velocity reaches 99% of the free stream velocity. Okay? Chalo. Now, boundary conditions. Because whenever this case will come, we have to apply the boundary condition and solve our three equations. What are the three equations? Mass conservation, momentum conservation, and energy conservation. This all again we are going to talk. That's what I was saying. There is so much to talk about today. Okay, but none of this is useful actually. This is also a problem. But chalo, theek hai. I am not demotivating you in any sense. It is all important because you need to know the flow of things. If they twist the question, then you have to go to the basics. Yes, this is kind of fluid revision as well. Yes. But there you do not have, this is hydrodynamic you talk, but you do not talk about thermal. Boundary layer, we are going to talk about thermal as well. Okay, chalo. Now, hydrodynamic boundary layer for external flows. What are the boundary conditions? At any x, at this much distance, okay, measured from the leading edge of the plate. Chalo. By this is that we all know, we have discussed. Is there any confusion in this? This is one of the boundary condition. Okay. Is there any confusion in this point as well? At y is equals to delta h, u is equals to 99% of u infinity. ठीक है, चलो. Now also tell me, I have told you one thing. Look, here we have del u by del y is not equal to 0. But at this point, velocity gradient is not there anymore. So del u by del y will be equal to 0. Isn't it? Okay. So this is again one of my boundary condition. Pressure gradient, we are not going to assume. We are going to assume pressure gradient is same inside the boundary layer and outside the boundary layer. We are going to cancel that. We are going to simplify our equation and we will remove that term. In fluid mechanics, you take that, I think. But here we are not going to take that. We will assume pressure gradient is same inside and outside the boundary layer. Okay? So, now, also we know that at y is equals to delta h, velocity will reach to its maximum. Velocity can never go, you can never go greater than u infinity. It can never go greater than u infinity. The maximum velocity that you can have is u infinity, and that is what we have observed at y is equals to delta h. ठीक है? Clear? चलो, let us move on now. So this is our boundary condition. We are going to use them later on. Now let's talk about thermal boundary layer. Oh, I'm sorry. Yes, thermal boundary layer for external flows. Chalo. So, okay, just one second. Yeah. Okay. Now what is happening here? Look. Thermal boundary layer is formed because of temperature gradient. Okay. So, let me take a plate here. Okay. Let me take a plate here. Solid plate. And it is at T surface or T wall. Sometimes in question they say T wall or T surface. Okay. Now a fluid is flowing. With U infinity and T infinity. Okay. So T infinity is ambient temperature. and it is uniformly distributed, of course, because there is no disturbances because of this T surface. T surface, there is no disturbances. Now, I am saying Ts surface is greater than T infinity, greater than T infinity. That means it is a hot plate and fluid is colder than the plate. It is a hot plate. So when this fluid is going to flow over this plate, it will be heating of fluid or cooling of fluid. Fluid will get hot, right? Fluid will absorb heat. Fluid will absorb heat from the, yes, heating of fluid. Now again, we all know that X is equals to, at this point, X is equals to 0 and Y is equals to 0. Now let me go to a particular X. Now the layer that is adjacent to this plate, the layer that is, one second. Okay. Okay. Now the layer that is adjacent to this plate will be observing a temperature of T wall, isn't it? Ideally, I am saying ideally. Of course, it will not assume Ts, but ideally it will absorb Ts. Okay. So at Y is equals to 0, can I say temperature will be equal to T of wall or Ts? Okay. Let me check what boundary condition I have taken. Then accordingly, I'll change my T wall I have taken. Okay. So it is TW. It is TW. Somewhere I have written TW, somewhere TS. I'm really sorry for this, but they both are same. Wall temperature या surface temperature. ठीक है, चलो. TW. Now, as you are going up, this temperature of the fluid is going to decrease. As you are going up, the temperature is going to decrease. Right? And at a certain point, it will reach to T infinity, or I can say 99% of T infinity. At a certain point, it will reach T of fluid will reach 99% of T infinity. Now it is not going to change. So there is no temperature gradient. Okay. So here it is how temperature is changing, and then it is not changing here. At this point, you have reached this point, and then it is same. So this is dt by dy, temperature gradient. Similarly, we can do that, okay, at different locations at X, and then we can join all of them, and we have this thermal boundary layer. Okay. Now we know that inside this thermal boundary layer, it is not equal to 0, and outside there is no temperature gradient. It is equal to 0. Okay. So this is the case of heating when there is a hot plate and fluid is at a lesser temperature than the plate. Okay. Now, so thermal boundary layer is defined as a thin layer formed over the flat plate inside which temperature gradient are seen in the normal direction. Now you see why the hydrodynamic boundary layer was formed. Can you tell me? Because at the surface u was 0, and as you were going up u was increasing, so there was velocity gradient from y is equals to 0 to y is equals to thermal hydrodynamic boundary layer thickness delta h. Okay. Now why thermal boundary layer is formed? Because of temperature gradient. By at the surface temperature is T wall, and far away from the surface it is T infinity. So how the fluid temperature is changing from T wall to T infinity? That is what temperature gradient is showing near the boundary layer, near the flat surface. And that is the reason, because of the temperature difference from T wall to T infinity, a thermal boundary layer is formed in the direction normal to the flat plate. Okay. The temperature gradients are found due to heat transfer between the temperature and flowing fluid. Now, because of temperature difference is there, so heat transfer is also happening. Now, we know that at this point, by y is equals to 0 and t is equals to t wall, and at this point y is equals to certain y, temperature gradient is hyperbolic. This one is hyperbolic, but one of them is parabolic as well. We are going to talk about later. Okay, chalo. So when it is changing, so यहाँ पे क्या है, y is equals to delta T. This is thermal boundary layer thickness, and here T is equals to 99% of T infinity. So it is the arbitrary defined as the distance measured perpendicular to the plate surface in which the temperature reaches 99% of the temperature of the free steam fluid. Okay, so this is what you have. Now here y is equals to 0, P is equals to T wall, and T is equals to 99% of T infinity. Okay, chalo. What about cooling of fluid? Now here the plate is at Ts and this is T infinity. Now here Ts is less than T infinity. Means fluid, hot fluid is flowing over the hot plate. Okay, a hot fluid is flowing over the solid plate. Of hot fluid is flowing over the solid plate. Now solid plate is at lower temperature than hot fluid. That means that fluid will give heat to the solid plate and get cold. So it is cooling of fluid. Okay, so now at the wall here, by temperature will be lowest because Ts is the lowest temperature in this condition. So here T is equals to T surface, and as you go up you will go close to T infinity. The temperature is increasing, but at the surface T is equals to surface temperature or wall temperature. As you are going up, the temperature is increasing, the temperature of the fluid is increasing, and at this point temperature at y is equals to thermal boundary layer thickness, temperature is equals to 99% of T infinity, and after that there is no temperature gradient. So this is parabolic. Okay, here at this point T is equals to T infinity. Now inside this thermal boundary layer, dt by dy is not equal to 0. Outside dt by dy is equals to 0. I'm sorry, I have written it wrong. It is equals to 0. Okay. Now these are two cases. When we draw thermal boundary layer, these are two cases: heating of fluid and cooling of fluid. But the boundary condition is not going to vary much, because whatever condition you are taking, y is equals to 0, T will be wall temperature only, surface temperature only. And at y is equals to lambda T, T is equals to 99% of T infinity. Also, at this point, after that, there is no temperature gradient. And of course, you will get the maximum or minimum temperature at this point. Maximum or minimum temperature at y is equals to delta T. So these are my boundary conditions. Is it clear? Of course, I have skipped some few things. I have I'm just trying to give you very minimum information for this.
Sorry, is this?
But, yes. 1 second. Yes.
Thermal boundary layer was up to 99% of temperature difference or otherwise it will be 0.99 T infinity.
Yeah, it is 0.99 means it's in percentage actually, 99% of T infinity. That means we are very, 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 very close to T infinity. We are almost at T infinity.
Okay.
If I say it is 1, if I replace it to 1, that means t is equals to t infinity, right?
Okay, sir.
So we are very close to t infinity actually. ठीक है ना? Clear? चलो. Now now whatever boundary conditions we have defined, for each condition we have to apply into our three conservation equations. The first is continuity or mass conservation equation. Now what we are assuming, by steady two-dimensional and incompressible, two-dimensional we are taking, okay, unit depth of element. So that means inside the plate we have L. Whatever is inside, it is unit depth, means 1, perpendicular to the plane of figure, and real fluid flow. Okay, so let us take a small element of fluid inside this boundary layer thickness. Okay, in this region I am taking one fluid element, because this velocity gradient will not be forming here only, it will be forming everywhere. It will be wherever you go, it will be forming. So I can take from anywhere. This fluid element I can take from anywhere. Okay, chalo. So let me take a fluid element from this inside this boundary layer thickness. Okay, chalo. And I am saying this is dy. I have A, B, C, D I have named. Okay. And this is my dy, because it is very small element whose height is dy and length is dx and depth is 1. Okay, chalo. This is 1. So what can I say? Mass conservation is whatever is going in will be equal to going out. So rate of mass flow in the control volume is rate of mass flow out of control volume. Okay, so where it is entering, it can enter in x direction and y direction. So in x direction from AB, it is entering as density velocity into area by mass flow rate is what? Rho A V. And V is what? V is velocity in y direction in x plane. Okay, so it is y direction, right? If we talk about vertical direction, it is y direction. So V is the velocity or in y direction in x plane. This is x plane, right? This is x plane and y direction. Okay. Similarly, in dA plane, in dA which is y plane. So in y plane, u is the velocity in x direction in y plane. Again, do not worry about all these details. It is not very important from exam point of view. But you just need to know that from this it is entering in y plane and this is entering in x plane. Okay. Now this is exiting, of course. Rho area will remain same and this is change in velocity. If any change has come inside the fluid element, in the velocity it will be accumulated in this form. Okay. Yes, ui plus vj, that is correct. Okay. And in x direction or x, so this is your change in u if anything has come. Okay, in y plane and x direction, okay, because here something will be happening, right? You will be giving some energy, some fluid intermixing will take place, some energy will be transferred from x to y direction. Okay, so because of this change will come. Okay, so what is in, by from AD it is coming, from AB it is coming, right? This AB it is coming and AD it is coming, and BC it is going out and CD it is going out. So simply what we are going to substitute this all these equations here. Look, there is no point, I am not going to do it. Okay, just substitute it here and so many things will get cancelled. For example, rho u will get cancelled, this v and this v will get cancelled, only this will be remained, and then you divide everything by dx and dy and finally you will get this equation. This is your quantitative equation or conservation of mass equation. Again, I am not going to do it. Okay, if you want, I can send you. I have a PPT that we have done earlier. I mean, not I have recorded few sessions. So if you want elaborate derivation, I can give you that. Okay, chalo. Then this is your continuity equation, very important. Now, momentum conservation equation. Momentum conservation equation. So Newton's second law is basically the basis for momentum conservation. We all know, even Navier-Stokes equation come from this, right? So it says force is equals to mass into acceleration. Whatever force is coming in all the directions is equals to mass into acceleration. Okay, now we are taking only in x direction. The net force acting on the control volume is equal to the net rate of momentum outflow from the control volume. So net force in x direction is equals to rate of change of momentum in y direction. Forces, what are the forces that are working? Surface forces and body forces. Now surface forces are pressure forces and viscous forces. And of course, we are going to cancel our pressure forces later on. So we are not going to consider our pressure forces. Okay. Body forces are gravity, electric, and magnetic forces. Now in our analysis, body forces are negligible compared to surface forces. So this is what we are going to cancel. We are not going to consider this. Okay. Now delta M is equals to rho into delta V. So rho into this is delta V. Delta X, delta Y, and depth is 1. Okay. And acceleration is equals to du by dt. Du by dt. Okay. So it is du by dx. So we are going to differentiate x. We are going to differentiate u in x and y direction. X and y direction. So du by dx into u plus du by dy into v. Okay. Now what about surface forces? What about surface forces? By pressure and viscous forces. So pressure forces are acting in this direction. Now these are compressible forces. So it will be negative. And these are shear forces. It is tau plus del tau del y into d. Okay. So net change in viscous forces is equals to this minus this into area. So these are forces. Okay. Stress into area will be force. Stress into area will be force. Stress into area. Now this is delta t by delta tau dx dy 1. When you simplify this, net change in pressure force. Now this is p dy into 1 because it is applied in y direction. Y plane, I am sorry, and this is x plane dx. Okay, minus from the opposite direction. So because it is compressible, that's why I have written this way. And you will get minus del p by del x del y 1. Simply you are going to add this and this. So you will get this. You take this common and you will get this. Okay. Now we are neglecting the pressure differences. Pressure in the boundary layer we are assuming is pressure in the free stream. So we are cancelling this. You are going to get surface forces as this. So surface forces and body forces we have already neglected. This is already equal to 0. We have defined earlier this here, these two things. So we are going to substitute this here, and surface forces we are going to substitute. We are going to get this, and then we divide everything by dx dy 1, and finally you will get this. Now if I divide mu, we know mu is equals to mu by rho. So we will be nu del square u by del y square. This is your momentum conservation equation in x direction. Again, of course, I have skipped few steps. I have skipped few details. But again, even this derivation is not important. I could have just given you the resultant, the final result. Okay. Chalo. So this is your momentum second equation. First was continuity equation. This is second equation. Third is energy. Now we are going to do an energy balance. Steady two-dimensional incompressible flow. That means Rho is equals to constant. We are assuming constant fluid properties. Unit depth. That means depth is 1. Depth is 1. Okay, ठीक है. 1 second. ठीक. No. अभी तो I don't think we have even reached half of my slides. I don't know. Probably we have. Today we have more than 50 slides. Chalo, let's move on, Shruti. Okay. Chalo. Negligible heat conduction in the direction of flow. Okay. So heat conduction is not happening in x direction. You see, heat transfer is only happening in y direction, in this direction, not in this direction. That's why we are not considering del t by del x. This is equals to 0. We are only considering del t by del y. Temperature gradient is only in y direction, not x direction. Okay. And work done due to viscous shear stresses effects is equals to 0. So let's do an energy balance. Okay. Now look, energy can be transferred because of work and heat. Work, we are not doing any work here. Only heat exchange is taking place. So it can take place because of heat transfer or mass transfer. Similarly, it can enter from mass and heat form, out also heat form and mass form, out also mass and heat form in y direction. This is in y direction, this is in x direction. This is in y direction, this is in y direction. Okay, chalo. So energy in that is happening is first of all in x direction because of mass, because of heat. In y direction, energy in because of mass, because of heat. Now this is energy out because of mass in x direction. This is because of heat in x direction, as I have showed you earlier. This is because of mass in y direction, exit. And this is because of heat in y direction. Okay. Now there are again some steps are there. You can simplify and rewrite this. Of course, you can directly cancel this. Ey, Qx, Qx, Qy, Qy. Other simplifications will be needed, and you can write this equation. Okay. Now mass flow rate is what? Mass flow rate is what? Rho A V. Velocity. Here we are taking as U. Okay. So you can write this as this mass flow rate. Energy, how can you write? By CPT. CPT. Mass energy is equals to m dot Cp T. So this is mass flow rate, this is energy in x direction. Okay, chalo, upon dx. And this is heat due to conduction at y is equals to 0. At y is equals to 0. Okay, so dt by dx. Dt by dx, so it is in x direction, it is in y direction. Okay, similar things we can do here, and we can get this equation. We are just substituting the values, that's all, nothing else. So this is my equation. I can further simplify it. I can cancel few terms here, and I can get my equation as this one. Now, since I am neglecting heat conduction in x direction, so this will be cancelled. So only this is remained, and this is called as thermal diffusivity. Now this is my energy conservation equation. Okay, so finally I have got these three equations. My conservation equations are mass conservation, momentum conservation, and energy conservation. Okay, I know it could be slightly boring today because I cannot do anything. These are only these things. Okay, not, it's more mathematics than concept. Chalo. Actually, concepts are also there. I cannot just say concepts are not there. But in order to go to this concept, we have to drive it. And to drive it, basically, it is going to take much longer time. Then, in fact, just to drive them takes more amount of time. if we start driving our momentum equation, Navier-Stokes equation, it will take much more time. And in the same time, we can even finish our convection. Whole convection we can finish. Okay, chalo. Now look, we have defined our equations. We have defined our conservation equations. We have defined our boundary conditions for external flows. Now it is time we start solving them. And what is useful for us is the solution. The equations that we are going to define is more important for us in the solution part. Okay, whenever we start solving questions, we need the equations that comes in the solution. Okay, chalo, theek hai. Now, what is the objective? What is the objective? So we are solving hydrodynamic boundary layer equation. Okay, so first objective is to determine hydrodynamic boundary layer thickness. Then to determine that velocity distribution or velocity gradient du by dy, how it is changing in y direction, how velocity is changing in y direction. Then we have to determine stress distribution. So we can determine tau by substituting this here. This is the objective of solving hydrodynamic boundary layer equations. Then we will go to thermal boundary layer equations. ठीक है, चलो अभी let's talk about hydrodynamic boundary layer equations. Okay. Now let us take our two equations, two conservation equations, mass conservation and momentum conservation, and steady incompressible laminar flow of a fluid with constant properties over flat plate. Now Blasius has solved these equations experimentally. And given a equation for hydrodynamic boundary layer thickness delta H, which is 5xy Reynolds number. 5x by Reynolds number. Now, what is Reynolds number? Rho Vd by mu. Now, you have to understand whenever I talk about x, this is your local. That means, look, this is your flat plate. This is your hydrodynamic boundary layer. Okay. Now, whenever x is there, it means the local variable. What do you mean by local? That I am talking about at a particular x. I am talking about a particular x. Okay. And what is the boundary layer thickness here? Or what is the Reynolds number at this point? But when we talk about later on, we will come to average values. Then we will integrate it to the whole length of the plate. Whole length of the plate. Okay. So it is the local values. Whenever I talk about x, for example, I have mentioned x here. It is the local variable, local Reynolds number. Okay. So by Reynolds number is what? Rho V D. Now D for flat plate is L. Okay, length. And I am talking only at a certain x by mu. So we can put it here. And we can, do a little bit modification here. So mu by rho is equals to this, and x can come out and go up. So finally, I will get this equation. This equation is useful. This equation is useful in solving questions. Okay. Again, it is hydrodynamic boundary layer thickness. 1 second. Sorry. Okay. Hydrodynamic boundary layer thickness. Chalo. Now, so our first objective is done. Now it is time to determine del u by del y. So we know that it is parabolic. We know it is parabolic. Okay. So what we are going to do? We are going to take a parabolic equation. We are going to take a parabolic equation of u. We have defined a general equation of u. Now we will insert various a, b, c, d constant and see if it fits all the boundary conditions, So it's an iterative process. So what we are going to do? We are going to apply these boundary conditions here and see if it is satisfying. It is satisfying or not. So again, it is an iterative process, but we are not going to do that. But what we are going to do, we are going to find a dimensionless velocity profile by u upon u infinity is what? U value is also meter per second, u infinity is also meter per second. So it is dimensionless. It is dimensionless velocity profile. Or velocity distribution. But from here, I can see that u is a function of y. U is a function of y. So of course, I have achieved my second objective. I have achieved my second objective. Now, if I differentiate du by dy, if I differentiate du with respect to y, then how much would it be? By 3 by 2, 1 upon delta h, u infinity minus 1 upon 2 y 3y square upon delta h cube into u infinity. ठीक है, चलो, this is my del u by del y. Now I need to find out shear stress. Okay, so Newton's law of viscosity हमें ये देता है. Now I need to find out what is the shear stress, because it will be the maximum shear stress at the wall. So it will be d tau at the wall. It will be maximum shear stress. Mu du by dy, but du by dy at what? At y is equals to 0. At y is equals to 0. Because at wall, y is equals to 0. At wall, y is equals to 0. So let me substitute y is equals to 0 in this equation. If I put y is equals to 0 by this whole thing, du by dy at y is equals to 0 will be equal to 3 by 2 u infinity by this. Because this whole thing will become 0 because y is there. Okay? So this is what I have gotten here. So du by dy at y is equals to 0 is equals to 3 by 2, right? Yes, 3 by 2 u infinity by u infinity by the hydrodynamic boundary layer thickness. Okay. Now in order to find out shear stress, I need to multiply it by mu. So I will get shear stress as this. Shear stress as this. Okay. Now this is local wall shear stress. Physically indicate the frictional drag or drag resistance exerted by the fluid on the flat surface. Now I know delta H. I have defined it. What is this equation? Blasius equation. This is Blasius equation. One second, yeah. Okay. This is Blasius equation. I can substitute here. Okay. So if I substitute and further solve it, I will get shear stress as this. Okay. I can do that. There is nothing much to do here. Okay. But because I mean, there are so many things to do, I can actually do it. Tau wall is equals to 3 by 2 mu u infinity into 1 upon 5x upon Reynolds number x. Okay. So it is saying 0.3 rho Reynolds number x. Okay. So anyway, what can I do? I can do 3 by 2 mu u infinity 1 upon 5x upon under root rho v rho u infinity L by mu. Okay. In fact, we are talking about Reynolds number at x. So I need to put x here. I need to put x here. Okay. Now there is a mu here. There is a mu here. There is a u infinity here. There is a u infinity here. But it is an under root. Okay. There is a x here. There is a x here. You can cancel this. So you will get in the form of rho and u infinity, and then you will get in Reynolds number form. Okay, so you can, if you further solve this, you can remove this square root sign and solve this further. You will find got this equation. And I think 3 by 10, yes, this 2 into 5, it will 3 by 10, so it will be 0.3. Okay, so you can try to solve that and you will get similar equation. Of course you will get. ठीक है, चलो. Now, so this is what we have done is local walls, local shear stress. It is at a particular x that I have showed you. Now, in order to find average shear stress, we have to integrate this over the entire length. So when you do that, 1 upon L, 0 to L, 0.3, Reynolds number x, rho u infinity. Okay, when we do that into dx. Now where is x will be in the Reynolds number. So I need to open Reynolds number and I need to take the constant out. Reynolds number mein there is rho as well. Okay, so rho and rho will get cancelled. Okay, so basically what we are doing, whatever x we are going to get from Reynolds number, we have to take it out and we have to integrate with this dx from 0 to L. And when you do that, you will get that T average will be equal to 2 times of local wall shear stress at x is equals to L. Okay, now how do we calculate that? At x is equals to L. Now look, 0.3 is there. Under root Reynolds number. Rho v x आना चाहिए, but because we are talking about x is equals to L, so L mu and rho u infinity square. So if we calculate this and we put it here and multiply it by 2, we'll get T average. I know it is becoming a mess in your mind, but there are so many formulas, I cannot do anything. I have summarized it at the end, but I really can't do anything about it. Chalo, ठीक है. Local skin friction coefficient. So tau wall shear stress can also be given as CFX into 1 upon 1 by 2 this. So from here CFX is equals to tau wall 1 upon 2 rho infinity. Now tau we have already defined, local wall shear stress I can put here and I can simplify it, so I'll get 0.6 Reynolds number, under root Reynolds number. Again, in order to find out average skin friction coefficient, which is designated by CD, I am going to integrate that from x is equals to 0 to x is equals to L, and I will get 1.2. So again, it is same as shear stress as we have done. Okay, it is 2 times of local skin friction coefficient at x is equals to L. So whenever you are going to calculate your Reynolds number, you will put x is equals to L. Okay, is this clear? Chalo. Now thermal boundary layer thickness. We will quickly go over it. Now in hydrodynamic, our objective was to calculate hydrodynamic boundary layer thickness. In thermal, we have to calculate thermal boundary layer thickness. Then there we calculated du by dy. Here we are going to calculate dt by dy. And finally, we are going to calculate h. That was the main objective of the conventional analysis. From the beginning only, I told you h is my objective. Okay, so I can calculate H like this. By at the wall, Q conduction is equals to Q convection at the wall. Okay, and we will calculate by Q conduction is what? Minus Ka dt by dy at y is equals to 0 is equals to Ha T wall or T surface minus T infinity. So area and area will get cancelled. H you can calculate by this equation. So what will I do? I will calculate this. This is my second objective. Then I will put this here and calculate H. Then I'll calculate H and I will put it in Newton's law of cooling. HA Ts minus T infinity, and I can calculate my heat transfer. Okay, chalo. Now again here what we are going to solve? We are going to solve our continuity equation like Blasius did, continuity equation and energy conservation. And basically momentum. All three we need to solve here. And Prandtl actually gave one relationship between hydrodynamic boundary layer thickness and thermal boundary layer thickness. Now, if you remember in the very beginning, we talked about Prandtl number is equals to momentum diffusivity upon thermal diffusivity. So what was it actually telling you? It was telling you the thickness of hydrodynamic boundary layer and hydrodynamic and thermal boundary layer. Okay. So it is a function of this. So now it is giving you thermal boundary layer upon hydrodynamic boundary layer is equals to 1 upon 1.026 Prandtl number minus 1 by 3. It is again an important equation. I think I have marked important equations, right? First of all, look, this is important. This is important. Then it should be given you in question. If it is there, it is given you in question. You can calculate du by dy. Okay. But shear stress equation is important. This equation is important. Okay. And both of them are important actually. This one is important and this one is important. Also, this one is important and this one is important. Okay. Chalo. Now here, this one is again important. Okay. Now, this can be assumed as 1. So sometimes we also take it as this. Now, Prandtl number I can write as thermal upon hydrodynamic boundary layer. Prandtl number 1 by 3. 1 minus 1 by 3. I can write it thermal upon hydrodynamic boundary layer. Okay. Now I can also write it as minus 3. 1 second. I can write this as minus 3 as well, or I can write 3 as well. Okay. So it's basically giving you the same thing. But actually Prandtl gave you this. Prandtl actually gave you this. Okay. So in question, they may give you Prandtl number and give you hydrodynamic boundary layer, and you need to find out thermal boundary layer. Sometimes that kind of question may come. Okay. So first objective is to find out thermal boundary layer. That we have obtained our first objective. Second, we will do the same thing. Okay. So we again take a temperature profile. Okay. We will apply the boundary conditions and we will get a dimensionless temperature distribution. Okay. How temperature is changing in y direction. Okay. So again, I have got this. Okay. There, I think it is a similar equation. There we had u upon u infinity. u upon u infinity 3 by 2 y upon hydrodynamic boundary layer minus 1 by 2 y upon hydrodynamic boundary layer का cube. This is what. Now here y is replaced by both. Hydrodynamic boundary layer is replaced by thermal boundary layer. But now we have gotten how temperature is varying in y direction. So again we have got this. We have got this. This was our second objective. Now I need to find out third objective, which is heat transfer coefficient. So at wall I have defined this. How I have defined this? Q dot conduction at wall will be equal to Q dot convection. Okay, so this is my temperature distribution equation. I can calculate dt by dy at y is equals to 0. At y is equals to 0, which of course will be equal to, I think, 3 by 2 T infinity minus Ts upon, I think this is what you will get, because this portion will become 0. Okay, now I can substitute this here. So H is equals to minus K 3 by 2 T infinity minus Ts by thermal boundary layer upon Ts minus T infinity. Now if what I do is, let me put it positive and let me swap the temperature values. Sorry, I have cold. I'm taking tablets actually, so it's slightly better. What I'm going to do, yeah, eraser. So let me swap this Ts and T infinity. So this and this will get cancelled, and you will have 3 by 2 K upon thermal boundary layer. Okay. Now I do not have any isolated definition for thermal boundary layer. Prandtl actually gave me this. So only I can use this only. Okay. And here hydrodynamic is given by Blasius equation. So I substitute hydrodynamic here. I will substitute this here. And then I will calculate thermal boundary layer. And then I'll put this here and I'll calculate H. And then I put H. So if I do that, I will find out Hx is equals to this. How do you get Prandtl number and Reynolds number here? By Reynolds number was here and Prandtl number was here. So when you combined everything, you have gotten Hx in the form of Prandtl and Reynolds number. If you solve this, you will get it. If you solve this, you will get it. I have to do some other things. That's why we will move on. And anyway, you don't need it. You just need to know that this is what we will get. This is what we will get. Okay, chalo. Now Nusselt number is defined as HL or HD by K. Now local Nusselt number will be Hx and x upon K of fluid. Hx I have just defined. So if I put it here, so x and K will get cancelled and you will get Nusselt number will be equal to this. Okay, and average Nusselt number, as usual, I am going to integrate it from x is equals to 0 to x is equals to L, the whole thing, and I will get 2 times of Nusselt number at x is equals to L. Okay, so average Nusselt number is 2 times of local Nusselt number when x is equals to L. Okay, so this is my average Nusselt number. Okay, so I know so many things have happened today, but this is the summary of it. Mostly question will be solved from these. I am not saying 100%, but most of the questions will be solved from these summary. Okay, now first of all, it is for external flows and it is for forced convection. external flows, forced convection, and laminar flow only. Turbulent flow definitions and derivations are very complicated. Okay, so they are not if they ask, they will give you the relationship in the question. Even though they would not ask you, but even if they ask, mostly they will give you the relationship. Okay, chalo. All these equations, all these formulas are only valid for laminar flow. For laminar flow, dimensionless number, temperature and Nusselt number relationship. What Nusselt number? Can you tell me what relationship are you talking about?
Sir, we express the Nusselt number as a function of temperature, na sir.
क्या? Tell me one more time.
We express the Nusselt number as a function of temperatures, na sir.
Nusselt number, yes, it is a function of temperature, of course.
No. I am asking for the dimensionless temperature we express, na sir. I forgot the exact thing.
Okay. But I do not think that we use it predominantly, even though I'll take a look. Okay, if directly relation is used. Otherwise, it is the flow of things that you do. You calculate first either thermal boundary layer, and then you calculate this, and then you put it here. Okay, to calculate H.
Questions are there, sir, in convection.
Okay. We will solve questions. I'll take a look. If there is any any derivation that I have left, then I'll give you the resultant of that as well. Okay, do not worry. I'll take a look. I will take a look on the questions. If any relationship is there, then I'll bring it in. I'll give you. Okay. Chalo. So we started. Look, we have defined so many things today, right? And in the beginning, when we started, our objective was to determine H. That was a very basic objective of all the analysis. Prandtl number do not vary with X. Prandtl number is what? Prandtl number is, of course it vary with X. Why it does not vary with X? Prandtl number is diffusion, no? Thermal boundary layer is going to change with X, right? So at a certain X, they are going to give you thermal boundary layer and hydrodynamic boundary layer. But you see, no, this thickness is changing with X. For example, hydrodynamic boundary layer. This is changing with X. Okay. Do we move on? Okay. No, this was the exact relationship that he gave. Again, there are other variations of this equation, but it is not very frequently used. There are other equations as well, other variations of this, but it is most predominantly used. Okay, chalo. So, and anyway, it is giving at you at a particular X. It is giving at a particular X. Okay. Chalo. So we started with hydrodynamic boundary layer thickness. Hydrodynamic boundary layer thickness is defined by Blasius equation. Experimentally, he defined this. Okay. Then velocity distribution, how u is a function of y, we have defined. Okay. Then we have calculated shear stress. Shear stress is equals to mu du by dy at y is equals to 0, and we have defined local shear stress. Then average shear stress is defined integrating from 0 to L. X is equals to 0 to X is equals to L. And local skin friction coefficient and average skin friction coefficient is defined. Okay. Similar thing we have do when we talk about thermal boundary layer equations. So temperature distribution is defined. This is dimensionless temperature distribution. And local heat transfer coefficient we have defined then. Okay. And then average heat transfer coefficient by integrating it from 0 to L. X is equals to 0 to X is equals to L. local Nusselt number by using H we have defined, and average skin friction. Okay, this is average Nusselt number. I'm sorry. Average Nusselt number. Sai, you do one thing. You send me that. Okay. Later on after the class, you send me that equation and I'll take a look.
Sir, I have
And
sent you now only, sir. I have already
okay,
sent
okay,
it.
okay. ठीक है, I'll take a look later on. ठीक है. Nusselt number. I'll take a look and I'll explain that if need be. ठीक है, चलो. So this is basically the summary of, and most of the things will be solved from these equations. Most of the things. What Vijay is saying, I'll take a look, and if need be, I'll explain. If it need further explanation, otherwise I'll directly give you. It could be something in between, some modifications we need to do. ठीक है, चलो. The last thing for today is Reynolds-Colburn analogy. Reynolds-Colburn analogy. Okay. Now it is basically gives you a relationship between momentum diffusion and heat diffusion. Okay, we have two types of diffusion, right? By velocity distribution is there and heat distribution is there. How they, it is basically the interface, it is relating both of them. 1 second. Okay, sorry, I was thinking I'm gonna sneeze, but chalo. So it is going to relate momentum or velocity distribution, diffusion, and heat diffusion. Okay, so it is relating two parameters. What? It is relating heat transfer coefficient, which is from thermal diffusion or heat diffusion, and CFX, local skin friction coefficient, which is from momentum diffusion. So to predict the value of local convective heat transfer coefficient Hx at a given location measured from the leading edge just by knowing local skin friction coefficient. So if SFX is given in question, how can you calculate directly Hx? That is what this analogy is all about. Okay. At the same location X, even when there is no heat transfer between the flat plate and flowing fluid. Okay. So it is given by Stanton number, Prandtl number 2 by 3 by CFX, where Stanton number is Nusselt number divided by Reynolds number upon Prandtl number. And we all know Nusselt number is a function of Hx x by k of fluid. So that means we can relate Hx by CFX. Okay, so let us see how we are going to do that. Okay, so look, local skin friction coefficient is defined by this equation. This is what we have already seen. And Nusselt number is given by Hx by k fluid and this. Okay. Now local shear stress is 0.332 by Reynolds number rho u infinity square. So if I substitute this here and I calculate and I simplify CFX, I am going to get this equation. Okay. Now in Nusselt number, now if I divide this Nusselt number by one Reynolds number and Prandtl, if I divide the whole equation, for example, look, I have Nusselt number x. I divide this by Reynolds number x and Prandtl number 0.332, Prandtl number 1 by 3, Reynolds number x 1 by 2 by Prandtl number and Reynolds number x if we have defined. Okay, so it will be just, we can do what? We can do minus 1 on the top. Minus 1. So this will be equal to minus 2 by 3. If I simplify it, 1 minus 3 by 2. So this is minus 2 by 3. And what is this? Reynolds number, how much? Minus 1 by 2, isn't it? Minus 1 by 2. So this is what we are getting. here. Now we have defined Stanton number as Nusselt number by Reynolds number x by Prandtl number. So this is my Stanton number, which I have defined as this. Now if you see this, this is Stanton number and Prandtl number. Let me bring Prandtl number the other side. If I bring it this side, then I can get this equation. Now if I compare this and this, that means Stanton number into Prandtl number 2 by 3 is basically CFX by 2. Okay. You have to divide then these equations. If you divide this thing by 2, then these things will be equal. Okay. So this is the relationship that we have gotten between Hx in terms of Stanton number. So this is a relationship between Hx in terms of Stanton number and CFX. So it is basically trying to merge the concept of momentum diffusion and thermal diffusion. So Reynolds-Corbin analogy is basically trying to make an interface or trying to make it is trying to correlate these two different phenomena, how they both are related. Okay. So this is what we had to cover in external flows. External flows was a small part, but we had to cover the basics, and then Heidelberg boundary layer, thermal boundary layer, energy conservation, mass conservation, momentum conservation, boundary conditions. So therefore it took a lot of time. Now because some basic has already been generated, so tomorrow we will not, in the theory part we are not going to take so much time. Okay. Now you tell me one thing. Tomorrow, do you need a long class with everything completed? I think 2.5 hours would be more than enough. If 2 hour 30 minutes maximum, I don't think we need 2 hour 45 minutes, but maximum it will be 2 hour 45 minutes. What about other people? Shruti and Sai, are you there? Just let me check. Okay, yes, tell me. Long class or 2 classes? Okay, long class. Chalo, theek hai. Otherwise, I need to come, for 1 hour class, I need to again take one more class, and we can close your HMT tomorrow. Okay. So tomorrow we are going to cover internal flows. We are going to cover free convection. Now I have checked the syllabus. Earlier I used to cover boiling and condensation. But it is not given in syllabus. It is not given, but not in the morning. Okay. Let's talk about that also. So we are not going to cover boiling and condensation. I was thinking of covering it, but then I did not see this in the syllabus. Again, I am going to compare it with old syllabus. So if I remember correctly, earlier it was specifically given in question, boiling, but now it is not given. So if it is not given only this time, then we are not going to cover this. If you still want to, I would recommend that you give it a read, because it's just reading. So I will give you PPTs for boiling and condensation. You just have to read it. How boiling happens, pool boiling, flow boiling, nucleate boiling. So how the whole phenomena of boiling takes place. Just it will not take half an hour to read those things, but you will get an overall idea how boiling happens and condensation happens. Okay. So I will give you PPTs that you can see. Now, after this, we will do numericals. So I think we are fixed on tomorrow a long class. Now tell me, what is a convenient time for everyone? What is the convenient time? Shruti is saying not in the morning. I also agree with Shruti, because today I am not feeling well. I took some medicines and probably I will be much sleepy in the morning. I have to take tablets evening also, before sleep. 8:30 p.m. What about Sai? I don't have any problem with any time. What about 12 to 2:30 something? Huh? So Sean, are you okay? 12 to something, or Shruti? Is 12 okay? 8:80 p.m. 8:30 p.m. चलो भाई विजया, we have majority of 8:30. Tell me. Are you agreeing with them? नून, अच्छा, you have aptitude class at 1. ठीक है. Sean says 1:30. Shruti says, अच्छा, Sean earlier said 8:30. Okay, check the time. I have no problem. You all, I don't want you to miss any class. Let us just, decide. Let me stop the recording and let's come up with a, convenient timing for all.